Hello everybody, welcome to the World of Control channel. I'm Mohammed, and in this video I want to design a feedback linearization controller for the inverted pendulum system that we uh, designed, and we defined and extracted the dynamic of it in the previous videos. Okay, Uh, as we know from the previous video, the dynamic of the system uh, is this equation here that we wrote the acceleration of the angle of the pendulum, and we extracted the dynamics. The feedback linearization controller is a controller that can cancel the nonlinear dynamics of the system such that we derive a linear system. In this simple example, if we consider our input tau equals to this term here plus a new term, that this first term here, ml squared times g divided by l times sine of theta, is the nonlinear term of the dynamics. And if we implement this tau here in the dynamic, we can see that we can arrive to an equation that is theta double dot equals to nu. And in this situation, the system becomes a linear system. So we can consider nu as a simple PD controller, like here, as I write here, minus negative k of p times e, that e is the error of the system that defined like theta minus theta desired, and um, minus kd times e dot, that is the derivative of the error. If we implement this tau in the dynamics of the system, we will arrive to the closed loop dynamics like this. And actually by regulating these kp and kd here, we can arrive to the performance that we wanted, and the system will be controlled in this situation. Okay, let's go to the simulation. We already have the dynamics of the system here and the error. So I will implement a MATLAB function here to code our controller here. I will rename it to feedback linearization. Um, and now we can import to it the E and E dot, and let's see what we need here for our controller. The params we need, and kp and kd, so we can code our controller. Okay, the output of the MATLAB function is tau, so we can write here tau is equal to, I will name non-linear plus nu. And we know that the nu term is minus kp times e minus kd times e dot. And the nonlinear term, nonlinear term will be ml squared ml square times g divided by l times sine of theta, that we need to um, import the q value here, that is the theta is the first element of the q, and non-linear, okay, I have a type syntax error here, non-linear is correct. Now ml do times g divided by l times sine of theta. And now we have the controller. Okay, we need to extract the ml and g from params of 2. Let me make sure that ml and g are, m is the first element, g is the second, and l is the third element. mgl, mgl params 3 mgl. And now we have our controller here. If we do not have any syntax error, it will work. Okay, the e here, we need a derivative, so I add a derivative here to derive from e and implement it to the e dot. We need the params here, and the q, that in this simulation is the x parameter. For now, I will import a constant to import the k of p and k of d. We can define kp and kd in many other ways, but now for this simulation, I will, for example, import the values, for example, like randomly here, so we can see the simulation, and import the tau, that is our input. Okay, we want to control our inverted pendulum in pi divided by 2 as theta desired. So we run the simulation and let's see if our controller works. Okay, we can see that our theta is converged to 90 degrees that we wanted as the theta desired, and the system has been controlled very well here. As an input, I want to generate a sine wave to see the tracking performance of the system. I will import a signal generator here and set the waveform as sine with amplitude of 1 and frequency of 1. Let's see how the system works. And now we can see that the theta is the angle of the system is controlled very good, but it has some very little errors here that we can actually optimize the controller to um, avoid such these errors. If we increase the values of Kp and Kd, actually we can obtain our um, desired, and we can see that the error will become more or less here. But we can use other methods to calculate and evaluate the value of Kp and Kd such that the error becomes very small and actually near zero, close to zero actually. Okay, I will increase it more to see if the error becomes very less. Exactly. We can see that the error is very small, such that we can do not consider it as a very um, big problem. But with increasing these two values here, we can see that the magnitude of the tau becomes more and more. Let's see this. I want to show the control input as a signal to see the maximum value of it. Okay, we can see that we need one just, and we can show the control input. Okay, this is the control input here, and this is this actual theta and the desired theta that is very nicely controlled. And this is the feedback linearization controller. Actually, feedback linearization controller is a controller that um, we can see the complexity of it in very big and complicated systems with more than, for example, 5 or 6 degree of freedom, such that we have a very enormous equations, dynamic equations, and also we have a lot of actually um, equations. So we can use the feedback linearization to cancel out the um, bad effects of the nonlinearities. Actually, okay. Thank you very much. Please subscribe the channel. I will make a lot of videos about the controlling and modeling different other systems, so you can watch my videos. Thank you very much.